Hello everyone, welcome to my channel. Welcome to a new series of CMOS Subsystem Design. As a part of this series, we will be looking into various aspects of CMOS Subsystem Design, uh, among which architectural issues are the first one. And as we progress through the series, we will look into many other parts like design of carry select adders and carry save adders, and also we will be seeing some basics of designing a multiplication system using CMOS. And apart from this, we'll also be looking into what is a transmission gate, and how do we design transmission gate, and how do we use this transmission gate in designing of D flip-flop and multiplexer circuits. So this is a brief about CMOS subsystem design series. So as a part of this series, today we will be dealing about architectural issues that we face in CMOS subsystem design. So before moving any further, the first and uh, most important issue for any system is performance versus power trade-off. So if you increase the power, performance will increase. But the constraint is you have to maintain good performance in low power, because nowadays if you observe, every system is battery powered, which will require less power, which should require less power to operate. So achieving high speed operation requires optimized circuit design. What does this mean is, when you are designing circuits, you have to make sure that the delay introduced by the circuit, or the parasitics introduced by the circuit, doesn't affect the high speed operation of the circuit. So, and also we have to make sure that the power consumption is less, because when we go for faster switching speeds, it often increases the power consumption, because in order for faster switching speeds, to reduce delay, we'll be adding so many MOSFETs in parallel, which in turn will lead to a larger power consumption, because as MOSFETs are added in parallel, like if you see a simple MOSFET, so if you go on adding them in parallel, you see what happens is, any MOSFET you can remember it as a simple resistor when it is on, let us say RD. So as you keep on cascading this RD, what happens is the overall resistance offered by the MOSFET comes down. So this will reduce the RC delay time. But what is happening here, as resistance is increasing, so I is equals to V by R. This I is increasing, which is in turn leading to the higher power consumption. So power dissipation. Coming to power dissipation, these CMOS circuits have dynamic and static power dissipation. What does this mean? So if you are familiar with CMOS circuits, whatever you see, like whenever you apply any input, you are getting an inverted output, right? So how does it work is, so let us have a CMOS circuit here. So we have a PMOS here and an NMOS here, and this will be VDD, and this will be ground. So if you observe the parasitics of the CMOS, here you will be taking the output, but due to a parasitic capacitance, you will be having something, let us say C load here. So what happens is, whenever your CMOS is switching from on to off, let us say initially the charge on the capacitor is 0. So if you are applying an input as 0, for the output to let us say you are applying the input as let us say the input as 0, so the output must be 1. So for the output to reach 1, this capacitor has to charge from 0 to full charge. So during this transition from 0 to 1 or 1 to 0, whatever the capacitor charging and discharging, that will require more power. So this will lead to dynamic power consumption of the CMOS during the charging and discharging of the capacitances. And static power consumption is, as I mentioned earlier, these are nothing but RD. So this can be static power consumption, and one more static power consumption is due to leakage currents. So what is leakage currents is, even if your MOSFET is off, it will conduct few like milliamps or microamps of current through it, which will lead to the static power consumption. And coming to optimization techniques, we use low power design techniques like clock gating and power gating. So what is clock gating and power gating? As the name says, clock gating. Gating is like you are giving a gate for a resource. Power gating. So you are giving a gate for a resource. So if you have, let us say, a whole system with, let's say, 3 modules in it, and let us say at a given interval of time only one of the module need to function at a time. So you will use clock gating to supply clock to only one module, so that module 2 and module 3 will be not supplied with the clock, reducing the power consumption. And coming to power gating, so you will directly disconnect module 2 and module 3 from the power rail, so that the leakage currents by the MOSFETs also do not constitute to the static power consumption of those modules. And the next thing is, for optimizing techniques, we'll scale the supply voltage. Scaling supply voltage is nothing but moving through or navigating through technology nodes. Like for example, 180 nanometer, 90 nanometer, 45 nanometer, 22 nanometer. So as you move down, you can scale down voltages, because for very less voltage only, the electric field is good enough to pull to make to form the inversion layer for conduction, or the minimal voltage will give you a good control on the gate region. So scaling down voltages also will reduce the power consumption. And coming to area constraints, any company will always look at area constraints, because silicon area is always costly. So designers will always try to minimize the size of components. Always trade-offs arise between compact designs and circuit complexity or performance, because as you go on make the design very compact and small, the performance will obviously get affected, because as you try to make the design very small, uh, there can be more issues like interconnect noise, or uh, thermal noise. Many issues start to arise. Coming to techniques to address these issues, so implementing efficient logic synthesis and layout design. So what does this mean is, let us say when you are designing a digital system, uh, we have in prior to the design of the system, we'll be writing RTL code, and then we'll be verifying it, and after that only RTL synthesis is done and layout design is proceeded. So while doing that, we have to make sure that we are implementing an efficient logic. And coming to using shared resource, instead of let us say every system is using every system is using a mux, but all the systems are not simultaneously using a mux. So instead of keeping a mux option for every system, you can keep one mux, and you can give a like chip enable for the mux, that will be controlled by each and every system, so that only one mux can be shared by whole system. This is a simple example of shared resource. And coming to interconnect design, so what does interconnect design mean in issues of architecture is, let us say you have uh, a small water tank, and you need to fill a small bucket. So it will take, let's say, X amount of time. But if you need to fill the same kind of buckets like 4 or 5, it will directly it is directly proportional to the number of buckets. So in the same way, let us say if you have a AND gate, and for AND gate, this output you have connected to inputs of, let us say, 4 gates. As I have mentioned earlier, in every input stage we have a capacitor due to the parasitics of the CMOS circuits. So now this AND gate, instead of filling only one bucket, this needs to fill 4 buckets. So while filling these 4 buckets, it will require 4 into X amount of time. This will lead to delays. So while you are making interconnects, we have to make sure that this kind of delays should be avoided or reduced. Coming to signal integrity, crosstalks. Like if you are familiar with communication protocols, if you take I2C protocol, it is very sensitive to thermal noise. Like even if you if this is a I2C protocol, I2C line, here you have a resistor, there is a high chance that you will not be able to read I2C data, because this resistor will will exert some thermal noise, due to which this I2C data lines may be tampered. And coming to power delivery, ensuring reliable power distribution across the chip without excessive IR drops. So what does IR drops mean is, IR drops is nothing but similar to I square R losses. So whenever you are traveling across a chip through an interconnect, the interconnect will have a resistance R. Let us say here you have a device 1 D1, and here you have D2. When you are connecting those both with a simple wire, we assume that this has no resistance, so effective voltage drop across this is I cross R, which is 0. But in a real world this has some resistance, so I cross R is not equal to 0. So if here we have V, here we will have V minus delta V. So as the interconnect distance increases, this delta V increases, so which might push this voltage receiving here to maybe unknown or undesired value. So coming to solutions, if you are maintaining a large interconnect, it is better to use a repeater in order to eliminate these kind of issues, and shielding wires to reduce crosstalk. Like if you have two wires, you know that this might lead to crosstalk, you can shield them with uh, a dielectric or any kind of shielding method you can use. Coming to scalability with technology nodes, so simply to say, W by L ratio for a MOSFET is very crucial. So technology node always concentrates on L value of the MOSFET. Like what is L value is the distance between the P well and N well of the MOSFET. So if this distance between P well and N well keeps on reducing, what happens is the leakage currents between them keeps on increasing, because whenever you are reducing the P well and N well distances, that means even for a small change in electric field across the near in the gate region, that will lead to the formation of inversion layer. So even if there is a small or slight voltage, the leakage currents are flowing through the inversion layer is very high. So as I mentioned earlier, increased leakage currents, higher variability in device parameters due to small geometrics, design complexity grows. So these are some of the issues when you scale the technology nodes. Coming to clock distribution and synchronization, what does this mean is, let us say you have two sequential circuits, both must get clock at the same time. For example, if you consider UART only, for example, so if you are getting a if you are sending a, let us say if you are sending a signal to send the data, so you'll pull the start line down and send your bits and push back the start line. So this is what happens now. This is for UART. Now, what about SPI or I square C? So these both have something known as, they share the same clock. They carry the clock to both the devices. So if the clock is itself not in sync, or it is providing some delay, if the clock for first device is this and the clock for second device is this, so this amount of delay is very good and enough for leading to fatal errors. So this is known as clock skewing. And coming to power consumed by clock distribution network, so clock distribution network will always consume power. So in order to reduce the power consumed by the clock distributed system, we use something known as CTS, clock tree synthesis. In this, what we do is, we'll analyze all the modules that needs the clock, and we will maintain a particular network of clock distribution system which will consume very less power, and in the same time reducing clock skew and providing clock for every system. And also we can employ asynchronous design techniques to avoid global clocks in some subsystems. So for example, you have you need to like interchange data between two modules, and you have freedom of choosing a communication interface. So it is better to go for UART, because it is, as it is asynchronous, you need not sync the clocks, or skewless clocks is not required. So coming to reliability issues, process variation. What is process variation is, for example, you were continuously manufacturing your products with TSMC, and suddenly you wanted to change it to TI or MIT or some other manufacturing foundry. So this change in process also will affect the transistor's threshold voltage and length of the transistor. This will indirectly or directly affect the design parameters of our design. And coming to aging effects, transistors will always degrade over time due to phenomena like bias temperature instability or hot carrier injection. So soft errors include radiation induced errors, like you have a chip and uh, due to some random reason some alpha particle or some particles get hit on the chip, so that will flip the values in the memory cell. Like if you have a memory cell and 0000 everything is 0, so if it is got hit by an alpha particle, the 0 might change to 1, which means that data is tampered which is not intended. So this can be avoided by incorporating some error correction mechanisms, like cyclic redundancy check you can use for the integrity of the data present inside the memory, and you can use something like Hamming distance or Hamming codes for correcting 1 bit errors, and you can use many other techniques also. And designing for fault tolerance with redundancy. What does this mean is, even if the system goes wrong, your even if something goes wrong, your system must be able to withstand that small amount of error or small amount of fault. Like if only one input is you are giving wrong, it shouldn't lead to whole system failure. And power delivery and management, we have to always make sure that efficiently we are delivering power to all the subsystems without significant losses. Because for example, you have a low dropout voltage regulator, which will require continuous supply of, let's say, 3.6 volts. But due to your poor planning, suddenly some or the other day this 3.6 volts has dropped to 3.3 volts. So if this drop to 3.3 volts, you cannot guarantee the LDO output will be 1.8 volts. So if this is not 1.8 volts, this will change the whole design system parameters, because digital one is 1.8 volts for your system. So if this supply itself is not 1.8 volts, none of your subsystem will reach 1.8 volts. So none of your subsystem will not have a strong one. So not having a strong one is a big disadvantage, because when it is transmitting data between modules, this might lead to errors. As I have mentioned earlier, voltage drop and IR drop in power distribution networks can degrade performance. So you are having an interconnect with some resistance R. Here you give V, here we get V minus delta R. So this needs to be avoided. So in order to avoid this, we can use different methods for uh, minimal interconnect routings. So we need on-chip voltage regulators to get accurate voltage values for digital 1 and digital 0. And we also need to have power domains for selective power management. Like what does this mean is, like let us say you have a bigger system, you have in that subsystems you have, so one might be working at 3.3, one might be working at 1.8, but your power management system should take care of supplying 3.3 volts and 1.8 volts for both the systems. So coming to temperature and thermal management, as your chip is growing in complexity and design, what happens is sometimes as your design progresses, there might be some areas where in which the chip will be radiating too much of temperature. It might be due to interconnect resistance, or it might be due to the design itself. So in those areas, you have to make sure that that area is being exposed to the body, and that body is properly cooled by using a heat sink, or depending on the amount of heat it is being produced, you can go for either vapor cooling system. Different cooling systems are there. For example, if you take your phone itself, some phones have vapor cooling system, some phones have just air vents, and Asus ROG phone will have a separate venting system, where in which it will allow it has a proper window cut on the phone, so it allowing air to flow directly onto the processor. So this kind of techniques, they always take care for thermal well-being of your chip. Coming to testability and debuggability, no matter how good you design your chip, but if it is not testable, it is a worthless scrap. Because, for example, you designed a very good chip, but suddenly it is malfunctioning. So there must be a method or provision provided to the chip, so that the manufacturer or the consumer is aware of it, and also he or she should be able to debug the chip functionality. So for that, we have something known as design for testability, where in which we take into consideration of many parameters and design our chips, so that we will try to ensure 100% test coverage. And also we have something known as built-in self-testing modules, wherein which the let us say this is your system, and it has a small subsystem which is named as built-in self-test. So it has a certain test vectors that will which is hard coded into it. So it knows key when I apply these test vectors, my output should be this. So if you are not getting the desired output, that means there is some issue with my system. So it will continuously apply the test vectors, get the output, and analyze the performance of the system. So, in summary, architectural issues of CMOS subsystem design require continuous balancing of performance, power, area, and reliability. So, a designer must always balance between these four parameters to ensure that the chip coming out of the designer hands is like balanced among all these four parameters. So if you like this video and find this informative, please do like my video, share it with your friends. If you have any further queries or suggestions, do comment in the comment section, and please don't forget to subscribe to my channel TechTalks. Thank you.